看的是第7章 Filter Design Techniques. Okay, so we're going to talk about how to design filter. Well, if you want to talk about how to design filter, first of all, we need to say what kind of filter we would like to design. Well, there must be some kind of a desired filter that we would like to have, right? First, we need to have some desired filter that we want to have. Then we can talk about how to design. So first thing first, what is the kind of filter that we would like to design? We need to specify the filter that we want to design. And that's called filter specification. If I tell you the filter specification, then you know the kind of filter that we want to design. So the filter specification usually look like this. We would have something called passband edge, stopband edge, omega P, passband edge, and stopband edge. EDGE omega S, okay. There will be something called passband edge, stopband edge. And then in the passband, this is where our filter is going to be. And in stopband, this is where our filter is going to be. Right here, this is called omega 2. And there is something called passband ripple size. That will be delta omega 1. And there is a stopband ripple size, delta 2. Okay. So when we talk about filter specification, it's basically these 4 numbers, omega P, omega S, delta 1, and delta S. And it says that in this passband, suppose we want to design a low-pass filter, then this is where the passband is going to be. The passband can only in this range, and the stopband can only be in this range. Okay, so let me write it down. In the passband, the filter that we would like to have, well, usually what we specify is the magnitude response. Okay, just the magnitude response. For most application, the magnitude response is the thing that we are concerned with. So in the passband, the magnitude is in this range. Okay, for omega, that's equal to omega P. And in stopband, the magnitude is less than or equal to delta 2 for omega between pi and omega S. And when we specify, we only specify from 0 to pi, because usually it's we are talking about real coefficient filter, and when we are talking about real coefficient filter, we only talked about the frequency range between 0 and the pi. Okay, right? And in between, we said this is a transition band, omega P to omega S. That would be the frequency range that we say the transition band. The transition bandwidth is delta omega is omega S minus omega P. Okay, so let's try to draw an example that satisfies this specification. So let's see, let me draw another one. Okay, right here we have omega P here, right? And then omega S, and this is delta 2, and this is delta, this is 1, and this is minus delta 1, okay? Alright, So there we go, that's the specification. Our magnitude can only vary between 1 and 1 minus delta 1 in this passband. So let's say this is the magnitude response, like so. And then we check to see if it satisfies this is specification. Okay? Between 0 and omega p, between 0 and omega p, it's in this range. Between 1 and delta minus 1 and 1 minus delta 1. Okay? And from omega s to pi, is satisfied, it's less than delta 2. Okay? Right, so that's a typical specification, right, for low-pass filter. If we have a low-pass filter that we want to design, then we specify the pass band, we specify the stop band, and we specify the pass band ripple size delta 1 and the stop band ripple size delta 2. And these 4 parameters together is what we call the specification for this filter. Right, so if you tell me the specification, then I know what you want to design, the kind of filter that you want to design. And then we can start designing it. Okay, and there is something called stop band attenuation. Stop band attenuation, how is stop band attenuation defined? It's like so. It's AS equal to minus 20 log 10 delta 2. Okay, that's a stop band attenuation. So for example, our delta 2 is 10 to the minus 2. Okay, then what is our stop band attenuation here? If delta 2 is 10 to the minus 2, then what is the stop band attenuation? 40, right? Okay, 40. Okay, or when delta 2 is 10 to the minus 4, then AS is equal to 80. Thank you. Okay. Now, we already have this stop band ripple size, right? We already have this stop band ripple size delta 2, right? And it's like 10 to the minus 2, 10 to the minus 4. Why do we bother to define a different name? Well, that tells us basically the same thing, right? If you know delta 2, you know what the stop band attenuation is, and if you know the stop band attenuation, you know what the ripple size is. Why do we even bother to define a different name, stop band attenuation, and then give it and say this is stop band attenuation? Why do we bother to do this? Why do we want to express it like this? Well, for that matter, sometimes when we look at magnitude responses, see, the magnitude response that I draw here, well, it's just the magnitude response, right? The magnitude response itself. But sometimes when we look at the magnitude response, we don't look at it just like this, right? We do something extra. How do we usually look at magnitude response? We usually look at it on a different scale, right? Log scale. Okay, we usually look at it on log scale. Why do we want to look at it on the log scale? Well, that's something similar to this, right? This is stop band attenuation. Is basically the ripple size in log scale with a minus, right? Why do we bother with log scale? Why don't we just look at it like this? What's so special about log scale? 可以压缩比例，所以你看到的东西不是它真正的那个 scale， 对不对？那有的时候你需要压缩的这个，这个算压缩吗？是算压缩或者是放大，嘛啊，就是你需要改变那个比例了之后呢，你才可以看得比较清楚。举一个例子来讲好了，比方说像这个例子，我们的 delta 2如果是10⁻⁴次方的时候。 Suppose delta is 2 is 10 to the minus 4. Then when we look at the magnitude response, right? We look at the magnitude response. This is 1, and this is 10 to the minus 4, right? And after you design the filter, how do you know it meets the specification? Now, after you design the filter, we need to go back and check, right? Oh, first you say, this is the filter that we want to design, right? This is the kind of filter that we want to design, and then you go ahead and design the filter. But after you design the filter, you need to go back, you need to plot the magnitude response and see if it really satisfies the spec, right? But if this is 10 to the minus 4, how can you see whether it satisfies the specification? This is 1 and this is 10 to the minus 4, right? So this is like, if this is 1 and 10 to the minus 4 is like this much. You cannot really see whether it satisfies the specification or not. So we need something else. And if we log scale, what's so special about log scale? Let's try to look at log scale. What does log function look like? The log function look like this, right? Log 10 x, and this is x. When x is equal to 1, it's equal to, this is 1, okay? When x is equal to 1, it's equal to 0, right? Right? And when x is equal to 0.1, when x is equal to 0.1, then it's equal to, if we say this is, we have an extra 20, then let's put 20 here, okay? If this is 20, then this is 20. This is 20, right? This is 20. This will be 20. And if this is 0.01, this becomes 40, right? 40 is here. And this is 0.01. Okay, so like this. So it sort of magnify it. It magnified it a great deal, okay, especially when x is small. Okay, so now we can see clearly. So when the ripple size is very small, we will be able to see clearly through the log scale. Right? So usually when in filter design, we look at the magnitude response, but we also look at the magnitude response in dB. And today we are going to look at how we can design filter. We're going to look at FIR filter design, when the filter impulse response has only finite coefficient, and the case that the impulse response has infinitely many coefficients. Okay. So, first, FIR filter design. FIR. Let's first look at FIR filter. Right. And if it's FIR filter, and this will be the Z transform, and let's say up to n, and this n is called the order of HZ, okay, the order of the filter. Okay, this n is called order of the filter, because when we look at the Z transform, it's H0 all the way to Hn, Z raised to the power minus n. So this is the power. So that's why we say it's nth order filter. All right, so when we look at an FIR filter and we want to design the filter to satisfy certain specification, what are we going to design? Coefficients. Yes, thank you very much. These coefficients. So it's basically how to design H0 to Hn and this n here and this n here. Okay, how to design n and also these coefficients. First we determine what's the n, what's the order that we need, and then we design the coefficients, okay? how to design n and these coefficients to satisfy the given specs. Okay, so that's the FIR filter design problem that we are trying to see here. And we will, well, in the textbook there are basically two types of filter design here. One is called window design, which we will explain more today. Okay, and then the other one is called optimum FIR approximation. Okay, we will start with window design. And we will see, and after FIR filter design we will talk about IIR filter design. Okay, so that's what we want to talk about today. So window design, when people start on designing FIR filter, they don't really have a clue how to design it. But they do know that ideal filter is the best, right? We know ideal low-pass filter. Ideal low-pass filter, with ideal low-pass filter, you will be able to get the ideal response, right? With the ideal low-pass filter. So let's recall the ideal low-pass filter. The ideal low-pass filter looks like this, right? Let me put a I here. This is the ideal low-pass filter, and this is the cutoff frequency. That's the ideal low-pass filter, right? Okay, again, we are talking only about from 0 to pi. And we know what the ideal low-pass filter look like. The impulse response of the ideal low-pass filter. It's sine n omega c and then n pi. Okay, that's the ideal low-pass filter. Well, if we can just have the ideal low-pass filter, then everything will be fine. There's no filter design problem to talk about, right? And it will satisfy the specification, well, with infinitely small delta 1 and 0 delta 2, right? With the ideal filter. But is there any difficulty implementing such a filter? Why can't we just use the ideal low-pass filter? Then we will satisfy the specification just fine. Is there anything wrong with the ideal low-pass filter so that we cannot use it? Is it FIR or IIR? FIR is like this. The impulse response is finite, right? This is called finite impulse response. So it's FIR. Okay, that's FIR, right? Finite impulse response. Is this so? And the other one, as opposed to FIR, it will be IIR. IIR will be infinite impulse response. So is this ideal low-pass filter a FIR or IIR filter? So it's IIR filter, right? Okay, so it's an IIR filter. And, well, but we know in IIR filter, right? If we have those rational transfer function, then we would get IIR impulse response, right? Right? Then, is this rational? Remember, all the systems that we implement are rational, right? So is this rational? Have we ever expressed the ideal low-pass filter in this form? No. It cannot be expressed in this form, right? Because this is not rational. Just look at the 0. The numerator would have the 0, right? The numerator would have the zeros. How many zeros does this thing have? We're looking at the zeros, right? Where are the zeros? Where are the zeros? Is this a 0? That's a 0, right? Is this a 0? That's a 0. So every frequency in the stop band would be a 0. And we cannot possibly have so many zeros. All right. So that's not even rational. And it's not rational. Is it causal? It's not causal either, right? Because remember, it's like the sinc function and the spread from minus infinity to infinity, and there's no way we can make it causal. So it's not causal. Okay, it's well, it's not rational, it's not causal, so there's no way we can implement this thing. There's no practical implementation of the ideal low-pass filter. But we still want to design an FIR filter, right? So what people think of at that time is that maybe we can use truncation. We know the sinc function look like this, right? And the impulse response here are samples of this thing. So we just take samples. And as we move to the two sides, the samples become smaller and smaller. So maybe it's a good idea that we just take a part of it. Just take a part of it. And then it will be a good approximation of the ideal low-pass filter. And we can expect that when we have more samples, would it be a better approximation? It should be a better approximation, right? Okay, so that's the idea. Truncation. We simply take a part of the ideal low-pass filter between minus L and L, okay? So this is minus L and this is L, okay? So we just take this part off, cut this part off, and that's our HN. It only has this part. And if we increase L, if we make L larger, then this will be more and more like this, because it would have more samples. Well, but then you may say that this is not a causal filter either, right? This is not a causal filter either. What can we do about it if it's not a causal filter? Well, we can always make it causal, right? For a causal filter, we can simply move it, shift it. We can just shift it. Then, if we shift it, does it have any effect on the magnitude response? It doesn't have an effect on magnitude response, right? You just delay it. Okay, so the magnitude response will stay the same. Let's try to understand this. Well, we can say that in the time domain that we truncated to get a FIR filter. But how would the frequency response behave? Okay, we can expect that if we get closer and closer to the ideal low-pass filter, but in what form? And how does this length, this L, will determine how many samples that we truncate, right? How does this L or this length would affect the approximation? How does it look like in frequency? So that's the thing that we would like to find out next. So let's try to look at it from the frequency domain. Let's first understand what HN is. HN is simply a part of the ideal low-pass filter, right? So it's just like an operation that we have talked about. How do we take it? When we take a part, it's like a multiplying with A. It's HI, the product of hi of n and a window, right? And this wn is 1 for n less than l, and then otherwise, and 0 otherwise. And in frequency domain, oh, this is product in time domain, right? So in frequency domain, we would get convolution. It will be hi ej theta, and then w ej omega minus theta d theta 2 pi, 0 to 2 pi. Okay. It's the convolution of hi and the w. Okay. And we know what hi look like. That's what hi look like. Okay. And now let's draw what w is. W is the rectangular window, right? It's a rectangular window, so we know very well what it looks like. It's a window. What's the length of the window? 2l plus 1, right? It has 2l plus 1 coefficient. Okay, so, and why do we need to know the length? Because it will determine the zero crossing, right? 2l plus 1, 4 pi, 2l plus 1, all the way to 2 pi, and this is a theta, okay? This is a theta. This is a w, e, j, theta, right? And the others, on the other side, it will be minus 2 pi, 2l plus 1, okay? So it will look like this, okay? That's the rectangular window. How about the face part of this W? This window? What kind of filter is it? What will be the face of this window? It's symmetric, right? It's symmetric with respect to 0. It's symmetric with respect to 0, right? So when we look at the Fourier transform, it would have 0 face. It would have 0 face. Okay. So what I'm drawing is the Fourier transform here, not just the magnitude. It's the Fourier transform. Okay. So this is the Fourier transform of hi, and this is the Fourier transform of w, and we're going to convolve these two. Okay. So let's do that. So let's consider first that this is the hi, right? Let's first consider omega in the passband. This omega. When we're looking at the frequency response of h, e, j, omega in the passband, okay, in this range, then this is 0. And in the passband of hi, okay, when omega is in the passband of hi, what do? We flip it. First, this is minus theta, right? Minus theta, so we flip it, and then we move it to omega. Okay, so we flip it. It's a symmetric, so it doesn't matter, and then we move it to omega. Okay, so we move it to omega, and let's say this is the ideal low-pass filter. This is hi, e, j, theta, and this is a theta, and this is the, when omega is in the passband of hi, this is what we get, right? We multiply these two together. This is omega. Is it okay? When we are computing omega, that falls in the passband of hi. Okay? And then this is where w is, this is what hi is, and then we multiply them together and we integrate. When we multiply them together, because this is like a this ideal low-pass filter is like a window, right? So it will only the part that falls into the passband will get integrated. Is that okay? Only the part, this part will get integrated, not this part. Okay, not the part that's outside the passband. Okay? So as long as, and we can see that as long as, this is what we call the main lobe. And this is what we call the main lobe. This is what we call the main lobe. Main lobe. And this is what we call the side lobe. And we can see that as long as we have the main lobe, if we have the main lobe in here, then the result of the integration will be more or less similar, right? Putting the main lobe here and putting the main lobe here, we get more or less similar value. So we will get something that close to the area of this thing with some variation. And the variation will be caused by when we move some of the side lobe out of this passband, then that will cause variation in the result of integration. And then when we move the stop band, then what happens? And then we have the main lobe here. When omega is in the stop band of HI, okay, then which part get integrated? It will be, again, just the part that falls into the passband, right? So it's this part. And the value will be very small. Value will be small. Okay. And what's causing the variation? When some of the side lobe move out of the passband, so the part get integrated is a bit different. So the side lobe will affect the variation, will affect how much it varies when we do the integration. Okay. And we can expect that if the side lobe is very big, suppose the side lobe is very big, shoo, like this. The side lobe is very big, okay? Ooh, like this. Ooh, let me draw it a little bit nicer, like this. If the side lobe is very big, then will there be a bigger variation of the result of the integration? Then it would affect the integration more, right? So there will be, we can expect that then we will get a larger stop band ripple if the side lobe is bigger. Okay. So we can, from this formula and the picture, we can see that when we are computing omega that's inside the passband of HI, it will be a value that's pretty steady. And there will be a larger value, the area of this, okay? And when this thing moves to a different omega, then we get then we integrate again, we get the result of a different omega, and there will be some variation. And this variation will be caused by this stop band moving, the side lobe moving in and out of this passband. Okay, and when we talked about omega in the stop band, the part that get integrated will be the side lobe, some of the side lobes. And the side lobes again will affect how much variation of the variation in the result of integration. Okay, if we move this W a little away, we'll move it to a different frequency, then the side lobes that get integrated will be different. Okay, and they will cause some difference in the result. 好，我们刚才看到的呢是说，如果我们用 window 的方式来 design 的话呢，那么我们会是这个 ideal 的 low pass filter 跟这个 window 的 convolution， 在 frequency 里面我们看到的是这样子的啊。那 因为是 convolution 的关系嘛所以呢，我们的这个 window function 呢就会 convolution。所以当我的 window 是在这里面的时候，在它的 passband 里面的时候，那积出来的值应该就是差不多是比较大的，而且差不多。如果在它 passband 里面的话，它积出来的值都是差不多的。积出来的值都会是差不多的，大概就是那个，这个 main lobe 跟main lobe 的这个面积，然后再会扣掉加上一点这些side lobe 的影响。所以那当我的这个window 呢，如果是移到了这边 start band 出来的，到 start band 的这个地方 main lobe 移到 start band 的时候呢，它积出来的值应该就是小小的所以这个应该就是会对应到我的 filter 的 start band 的地方，我最后的 filter 的 start band 的地方。那如果我的 main lobe 在 pass band 里面的话，那积出来大概就是我的 pass band 的地方。OK， 那可是我们关心的是说我的 pass band 的 ripple size 跟我的 start band 的 ripple size 嘛那我的 pass band 的 ripple size 的话呢，会有受到什么影响呢？因为当我在这个里面的时候，当我在这里面的时候，我积出来的值差不多。可是当我在这里面移动的时候，当我的side lobe移出去的时候，这时候就会对我的积分的值产生影响了。那这时候它就会变成它有一个上上下下，就是我们的 ripple。那到了 main lobe 到了 start band 的地方的时候呢，这时候积到的只是我的 side lobe 的部分。所以如果我的 side lobe 比较大的时候呢，这时候我积出来的值就会有可能会比较大。所以我们可以看到的是说，这边的 side lobe 的话，就会影响到了我们的 start band 的 ripple size。那当然，这边的 side lobe 也会影响到我的 pass band 的那个 ripple size。OK， 那所以有 ripple size 有 ripple size 了，对不对？然后还有就是这个 transition 的部分 around omega c around the cutoff frequency of the ideal low pass filter. So we have the right here. Okay, this is the ideal low pass filter. And then we have the main lobe right here around omega c. So let me picture it right here. Just now we say the side lobe would affect the passband ripples and stop band ripple. How about the main lobe? Does the main lobe affect anything? Okay. So now first, when the main lobe start to move out, of the passband of HI, then the value, we would expect the value to be gradually decreasing, right? The area inside will be getting smaller and smaller. When it's right here, when the main lobe is right here, imagine the main lobe, say this is my main lobe. When the main lobe is right here, only the side lobe is out of the passband, right? So the main lobe still get integrated. And when the main lobe start to move out of the passband, then the area get integrated, it will get smaller and smaller. So the value will be smaller, right? So if the main lobe is wide, if we have a very wide main lobe, we would expect the transition to be large or small. If the main lobe is wide, we would expect the transition to be small or large. We would expect the transition to be a large transition, right? And if the main lobe is very narrow, like this, then it moves out quickly, then the transition will be a narrow one. Okay. So now let me write down the conclusion. The main lobe width affects the transition band bandwidth. And the side lobe would affect delta 1 and delta 2 of the final filter. Okay. And because the same side lobes would affect the passband ripple and will also affect the stopband ripple size. So the ripple size will be quite similar because they are both affected by the side lobe. Okay. And delta 1 is similar to delta 2. They are similarly on the same scale. Okay.